Recently, I've developed an interest in finance, so instead of being reasonable, I jumped straight into Brownian motion and Black-Scholes. How hard could it be?
Well, how hard can it be?
Don't say that!
Now to be fair, I'm not starting from absolute zero. I did take an introductory math finance course, but there's a difference between studying for exams, doing homework, and actually proving to yourself that you understand what's going on. So this video is basically my excuse to expose how little I actually know, learn as much as I can in public, and hopefully come out of this with a solid project at the end. No teaching, no pretending I'm an expert, just the process. Let's start. So, I opened a new tab and typed, projects to do with Brownian motion. One of the articles that caught my eye was called Simulating Brownian Motion and Stock Prices Using Python. That sounded exactly like what I needed, so I dove in. I realized something important when reading this article. Brownian motion is basically built on top of a random walk. A simple random walk in 1D works like this. You move forward by some distance d with probability of p, or a step back with the same distance with probability of q equal to 1 minus p. So, before I touched anything fancy, I slowed down and just simulated a basic random walk using the example code provided. Now that I had an understanding of random walks, I then proceeded with Brownian motion. The underlying random process which generates Brownian motion is the Wiener process, and it's defined like this. W0 is equal to 0, Wt has independent increments, and the increments are normally distributed with variance proportional to time, which means it starts at 0, the future doesn't care about the past, and the randomness grows with time. Using the example code, the output looks a lot like a random walk from before. That makes sense, as this continues that idea. Then I learned that by adding a drift term, the randomness will have some sort of trend. From the graph, there's still randomness, but now there's a general upward trend instead of just pure chaos. Now let's move on to geometric Brownian motion. This model is often used for stock prices. Geometric Brownian motion is defined as follows. Here I learned that this process shows up directly in the Black-Scholes model, where the key idea is modeling the log returns of a stock rather than the stock price itself. That's what eventually leads to option pricing. So one of my goals for this project is to simulate stocks, and with geometric Brownian motion, I can do that. Here I created a folder called sim for simulation. In it is GBM, geometric Brownian motion. Now let's proceed on with Black-Scholes. I wanted to understand the Black-Scholes model, so here I spent time reading articles and watching videos. I even saw a video from one of my favorite childhood websites to learn from, and that was Khan Academy. From this, I learned that I didn't in fact have to know of European options. This is the Black-Scholes formula for a European call option. The put is pretty much the same logic, just flipped around. And the formula outputs a fair price for an option contract. Alright, now that I understood it, I proceeded to translate the math directly into code. I wrapped everything inside of a Black-Scholes class with methods for both put and call options. Each computes the D1 and D2, feeds them into a normal distribution, and then applies the Black-Scholes formula exactly as written. At the bottom, I even added a put-call parity check. This was more of a sanity check to see if my implementation was consistent. Now, moving on to European and American options. I already have an understanding of these two types of options. European options can only be exercised at maturity, the expiration date, while American options can be exercised at any time up to and including maturity, so more freedom. I moved on to implementing European options first, as it was easier to implement. Monte Carlo pricing fits naturally here because European options depend only on ST, allowing the option price to be estimated at a discounted expectation over simulated paths. American options, on the other hand, took a bit of time. I found out that the Longstaff-Schwartz algorithm is commonly used for pricing American options. This is a more powerful Monte Carlo simulation. I read explanations online, watched videos, and even looked at a research paper. The part I struggled the most with understanding was the least squares regression step. Here, I simulated multiple GBM paths and worked backwards in time. At each time step, I compared the immediate exercise payoff with an estimated continuation value, which approximated using least squares regression. If exercising is more valuable than continuing, I exercise the option. Otherwise, I discount the future cash flow. With this, I can produce an estimate of the American option price. Now that I had a foundation, I was then able to start the final part of the project. Here I created 4 notebooks. The first notebook was simple. It was for data generation, where I simulated a stock acting as market history. The second notebook is about European options. In this, I took the historical stock prices, and at each point in time, it reprices a European call and put option using Monte Carlo simulation. As time advances, the remaining time to maturity decreases, and the option value is recomputed using the current stock price and the remaining time. Near expiration, the model switches to the exact payoff. The result plots show how the option prices evolve over time alongside the underlying stocks. The third notebook is about American options. The same logic applies here, where at each point in the market history, the option is repriced using the current stock price and remaining time to maturity. By using the Longstaff-Schwartz Monte Carlo method, it's able to identify potential early exercise points. The signals are detected whenever the immediate cash from exercising is higher than the model's predicted value of holding. That crossover point is my early exercise boundary. In the console output for one of the cells, you'll notice the put early exercise days is empty. That means for this specific path, the algorithm calculated that it was never worth it to cash out. The green dots at the end tell me that exercising the call option right then was mathematically better than holding on to it. As for the last notebook, this explores how machine learning can be integrated into option pricing from two perspectives. First, it prices an American put option using a Monte Carlo framework where stock paths are simulated via geometric Brownian motion, and a random forest model is used to estimate the continuation value at each time step, mimicking a machine learning version of the Longstaff-Schwartz method. This allows the model to learn when early exercise is optimal based on the state of the underlying asset. It priced our American put option at $8.01 using the random forest version of the Longstaff-Schwartz. Now, for full disclosure, I actually didn't come up with the idea of using random forest. Instead, I found out what was best online. I watched a couple videos and read the documentation, which was helpful for this portion. Next, it generates a large synthetic dataset of option pricing using the Black-Scholes formula and trains a random forest regressor to learn the pricing relationship directly from the option parameters. The trained model's predictions are compared against a true Black-Scholes price, and feature important analysis highlights which parameters most strongly influence option valuation. I got an R2 score of 0.99, which you can see in the reverse engineering scatter plot. The red dashed line represents a perfect prediction, and my model's purple dots are hugging that line tight. This basically means the machine learning model successfully learned the Black-Scholes formula just by looking at the data. Finally, looking at the feature importance chart, the model tells us exactly what matters. It figured out on its own that the stock price S and strike price K are the most critical factors for pricing, while the risk-free rate R doesn't have much of an influence. That's the project. If I missed something or made a mistake, please let me know. If there's something that I could do further to take this project to the next level, please comment below. Thanks for watching.